Okay, thank you very much all for being here in person and online. Speaker of today is AJS Simona Lo Franco from University of Modena, Reggio Emilia. Please, Simona, you can start.
Thanks a lot for the invitation and for the presentation. I'm really happy to be here today, and my talk will be on a mixed hybrid flux preserving element for the couplet problem of finite-strain poroelasticity. So we have developed in these years a couple of formulations that are alternatives to the standard for the study of the couplet problem of poroelasticity, especially for the study of biological tissues that goes into the finite-strain regime. So the poroelastic framework has been widely applied to biological tissue, despite the fact that it was originated in the field of geomechanics. We have few examples in literature of application, and such transferring of concept has been justified under the working assumption that if some material have a macroscopic behavior that is comparable, then we are allowed to apply the same computational framework to understand how they behave in their own mechanical behavior. However, the reality is far from being this simple. In fact, like even formulations that are stable and reliable when applied to the realm of geomechanics may have some convergence issue or not even converge when we try to apply them to the field of biological tissue. So some caution is required for this transferring of knowledge from one field to another. This leads us to a critical question. When we can say that an element or a formulation it's effective, when it's efficient. And Bate was trying to study this question, and he was saying, since a large number of different finite elements could be used, a natural question is, which models are the most efficient? And this question is difficult to answer. And he continues. Yeah.
Your problem you are referring are concerning the numerics, right? Not the modeling part.
No, it's concerned the numerics, okay, yes, okay. The computational point of view.
Okay, thank you.
Yeah, the mathematical framework stays the same, is the way that we address it through the use of finite elements in particular, like in general, a numerical tool, in this case, finite elements, to address it. No, yeah, the computational, like the theoretical framework is the same, is poroelasticity.
Okay, thank you.
No, it's fine. So in particular, we should note that the efficiency of an element, and this refers to finite elements, may to a large degree be problem dependent. So surely the class and the feature of the class of the problems that we want to solve have an importance in how much the element itself is reliable, stable, and efficient. And when we speak of biomechanics, we speak of features that are not in common with the realm of geomechanics, such as low permeability values. We are speaking of 10 orders of magnitude less with respect to geomechanics, like roughly speaking. Then we have the large deformation regime that in the case of biological tissue, we have to take in account because we go very easily into this regime. And then we have the fact that the system usually the tissue is super soft. So we have a high deformability of the system. So again, we need to have careful consideration. So we need to provide some care when we try to transfer this concept from one realm to the other one. Also because it has significant implication. In the framework of poroelasticity, we can address problems and scenarios that are pivotal for the study of brain, for example. And in the first image, we have a brain edema in which we have a swelling of the brain due to the pore pressure that increased locally. or the study, for example, of tissues such as intervertebral discs, that the mechanical behavior of them is really related to the flow of the fluid in and outside of the system. This leads to some research questions that we have tried to address during these years. First one, is there a dominant underlying cause under this numerical oscillation? So this spurious of oscillation that we have in the solution if we use standard formulation for poroelasticity. Can be they systematically prevented in such scenarios? And the second one, if we are able to do so, we can do so also in a computationally efficient manner. So we try to answer to the first question. First, we have a little overview on the theory of poroelasticity, so on the constitutive framework. It's a phenomenological theory. This means that we don't see, so we have this system in which we have a solid matrix with a network of pores that is perfused with a fluid that is allowed to flow in and out. We want to study the couplet problem of the deformation of this solid skeleton and the flow of the fluid inside. So being a phenomenological theory, we see the whole system homogenized. So we don't see locally where the fluid or the solid is. Instead, we focus on the effects of the coupling between the two phases. And these allow us the great advantage to apply classical continuum mechanics at the mesoscale and macro scale. It's based, this theory, on measurable macroscale quantities. This means that we have a set of boundary conditions that we can easily transfer to experiments. But on the other hand, being a phenomenological theory means that if we want to generalize this theory, for example, including other couplings with other fields, such as the chemical field, for example, or electrical field, we have to be very cautious. It requires some caution because it may lead to thermodynamically inconsistent formulation. So, but we stay with these two fields for the moment. Our variable of interest are the displacement and the stress for the solid part, the fluid potential, and the mass fluid flux for the fluid part. From this point to go on, I will use Lagrangian description of the system. So for this reason, you see the first Euler-Kirchhoff. But of course, everything can be written and described also in a spatial configuration. So in a standard way, the fields that are taken as primary variables are the displacement of the solid part and the pressure of the fluid part. Here you see this mu that stands for fluid potential, that is related with pressure through the density under the assumption of barotropic fluid. That is an assumption that is widely made in literature. Usually it's used pressure instead of fluid potential because it's made the assumption of truly incompressibility of the fluid phase. So in that case, the density became a constant and you can work with pressure. Here we prefer to be more general and so to use this fluid potential instead. But from a computational point of view, nothing changes. Then we have our field equation, so our balances and the constitutive relation. Here we work under the assumption that both the solid and the fluid phase are not intrinsically dissipative. So the only dissipation that comes is related to the flow of the fluid inside the solid skeleton. So with the motion of the fluid, but the fluid and the solid itself, they are not intrinsically dissipative. And then we have our set of boundary conditions, so the Dirichlet and the Neumann one. So the standard finite element approaches, as I said, they take displacement and pressure as primary variable of the system. And the first type that they were developed, they were continuous Galerkin formulation, and they were also called mixed one, because we had two variables that were working one independently from the other. The problem was that this element was pretty unstable, even in the geomechanical regime. And so some different formulations were developed to try to overcome this issue. The most used one is the so-called Taylor-Hood element. So the stabilized finite elements. Inside this family, you can have different formulations, but most of them, they are the gold standard, I would say, for addressing this kind of problem. Then you can have also 3 or more fields formulation that are inherently more stable, of course, but you pay the cost of degrees of freedom to add other variables to the system. You can have also discontinuous Galerkin formulation, but again, you pay the cost of the degrees of freedom, basically. The thing that all these formulations have in common is that choosing these 2 primary variables, displacement and pressure, leads to a saddle point problem. And this means that for the element, and so for the formulation to be stable, it must satisfy the requirements of the so-called IMSAP condition. There is a mathematical condition that the element must satisfy, and for the element itself, it translates to a certain difference in the order of interpolation between the field that we want to include in the element. So, and if the element doesn't satisfy these requirements, not only globally, but also locally, then we notice these convergence issues. So we have this spurious oscillation in the pressure field, or even the formulation might also not converge at all in some critical scenarios. Critical scenarios are for example, jumps in permeability, or very low level like value of permeability, or steep gradient in pressure, early time step. And these are pretty common in the biological realm. So for this reason, we have an interest to try to overcome this issue. And citing tight master, in especially the discrete, so the local IMSAP condition that is inherent to saddle point formulation is difficult to handle while keeping computational efficiency in mind. Because like you can try to go closer and closer with the mesh, so to refine a mesh, to try to assess a better solution, because certainly refine the mesh and refining also in the time step helps, but sometimes with complex geometry is computationally too much expensive to try to overcome with such solution. So our idea, following a path that was opened by Emilia, was instead of trying to stabilize the element, adding a stabilizing term, or working more through the mesh, so through a mesh refinement, is to swap one of the 2 primary variables to solve the PDE. So in this way, we pass from a saddle to a minimization principle, and we overcome, we circumvent the need to satisfy the IMSAP condition a priori, because we don't work with a saddle problem anymore. In this way, through a Legendre transform, we can recover 2 formulations. The first one is stress pressure, so stress fluid potential. The second one is displacement flux. So we change one of the 2. We rely on 2 minimization principles presented, one by Cossi, the other one by Mia. So we don't need to satisfy this requirement. However, we are now including as one of the 2 primary variables, a variable that is related to a balance law. So we need then to enforce strongly that balance law. This means that the variable, the element itself, must have the conformity to the HDiv class. The HDiv class, to speak with the words of Professor Brezzi, is modeling in such spacing is like eating cod liver oil. So it's not a joyful experience, I would say, because the HDiv space, and this leads to the second question, if we can do that in a computationally efficient manner, leads to tangent metrics that then we have to solve that are not sparse and not compatible with standard solver. We have to use some preconditioners before working with a standard solver. So, and it requires also way more degrees of freedom rather than a classical H1 space. So this means that we circumvent the need of satisfying the inf subcondition, and we have an element that is inherently stable. But on the other hand, we have an element that is computationally speaking way more expensive than a standard one. So we tried to give our contribute following this path, performing an hybridization procedure. So what we do is to break this HDiv space. And so we work with the HDiv space, like a sort of broken HDiv space inside each element. And we enforce the continuity of the normal of the field that must belong to the HDiv space just weakly. So we don't enforce strongly in the whole domain. We do enforce the balance law strongly just inside each element domain, and weakly like through the different elements and with the boundary. Of course, the other field it's approximated to a very standard way. So in this case, the other primary field is interpolated by standard isoperimetric function because we don't have special requirement for that. So from this idea, so to swap one of the two primary variables, reach a minimization principle, and then break the HDiv space through the use of a Lagrangian variable, we have developed these two different formulations. So the first one is the one that works.
Simona, I have a quick question. In the last slide, could you remind me what is lambda?
Lambda is, in this moment, is a general name to say Lagrangian variable. Okay. We will see the physical meaning of this Lagrangian variable in the two formulation, because like depending on the two formulation, it will have a different physical meaning.
Okay.
So the first element works with stresses and fluid potential as the primary variable of the system. You see that sigma, because this formulation is in the small strain regime, so is not the special description. So we work with pressure through the use of standard shape function, isoperimetric shape function. Then the stress function are described one element independently from the other, and it's expressed by a set of Cartesian functions that are self-balanced. So they express the whole possible statically admissible solution for each element. And then we use our Lagrangian variable that in this case assumes the physical meaning of displacement of the solid to enforce the codiffusivity of the stress through the element and with the boundary. So we start with the principle of Cauchy, and we perform a discretization in time under the quasi-static assumption, and we search for the increment. So we search for the incremental solution in this potential that is already incremental in time. We add this hybrid term, that is this one, that, as you can see, serves again to enforce weakly the codiffusivity constraint. So from the stationarity, we see as this generic lambda Lagrangian variable assumes the physical meaning of solid displacement. And these are the fields in which these are the functional space in which our field must belong. So we discretized by the use of standard isoperimetric function 1D, because each side is interpolated differently, separately from the other for the displacement. That is our Lagrangian variable. Then the stress is interpolated through this set of Cartesian functions that are referred to the local system of reference of each element, one element differently from another. And then our fluid potential is implemented in a very standard way through the use of standard 2D isoperimetric shape function. So this leads to this tangent matrix for the system. This tangent matrix is symmetric. Not only the part that is related to the stress, that is the one highlighted, but the whole matrix, the whole tangent matrix is symmetric. And this is like of great advantage for us, because usually in this couplet problem, especially in the large strain regime, we will see this leads to not symmetric matrix. So we cannot use symmetric solvers, basically. So in particular, having worked element by element for the stress-related part, this allows us to invert the first equation and to eliminate through a static condensation procedure the stress coefficient, this AE. And so this led us at the end of the day with a system that depends just on displacement, because we collect the pressure degrees of freedom inside the vector of the displacement, and we eliminate the stress. So this led us to a system that can be then plugged in a standard finite element solver for displacement. We have performed a few benchmark tests to assess the performance of the element. And in this case, we have the Terzaghi test is a very standard test for poroelasticity. So we have this column, is a 1D problem. Every boundary is undrained, just the top is drained, and we put a load on the top. And we see what happened. Here you find the comparison between the analytical solution and our solution with this element. Even for very early times, step that usually gives some oscillation for the standard finite elements, we see a good agreement with the fluid pressure. The same happens with this consolidation test, for which basically the problem is the same, but the load is just on half of the top. So the problem became 2D. And as you can see from the dotted line, the standard Taylor-Hood stabilized element, so an element that is basically the gold standard for this kind of problem, exhibits some oscillation, but instead this formulation is pretty reliable from this point of view. However, why we didn't push this formulation to the large strain regime? And this leads to the bonus question. Can we do this in the finite strain regime? Because like speaking of biological tissue, we cannot speak like of just small strain regime. This is pretty tough to do with a stress-based formulation, because we cannot work with a free strain energy density. We should work with a free stress energy density. And the inversion of the constitutive law, when it's feasible, because it's not always feasible, is pretty complex. For this reason, we have chosen to pass to the second formulation. So we swap the other two variables. In this way, we stay with the displacement, and we can address everything with the kinematic of the solid, and so follow a path that is already stable in the finite strain regime. So for this reason, the core idea of the element is the same. So swap one variable, then we break the HDV space, and we have our hybrid mixed element. And in this case, we change the variable and the position, like the spaces in which they belong. So the displacement now is interpolated through a very standard shape function, so isoparametric shape function. Then the fluxes, the mass fluxes, they are interpolated independently from one field, from one element to another, through the use of a set of polynomial functions. And then we use this time the fluid potential as the Lagrangian variable to enforce the normal component, the continuity of the normal component of the fluxes. Because this time we have to enforce the mass balance instead of the equilibrium. So we start again with the principle of Mie this time, that has a very similar structure to the other one. Of course, our primary variables are different now. So we perform a time discretization, and we incorporate the continuity equation directly into the energy functional. So this time, to enforce strongly every element domain, the mass balance, as you can see in the first equation, we have that the free energy density depends on m, that is the increment in mass of the fluid flow, because it's the natural variable for the free energy. Instead, we enforce the balance of mass, and so we pass from the mass to the divergence of the fluxes. And as you can see in the last equation, we see that the free energy density this time depends on the divergence of mass of fluxes by enforcing directly the already discretized in time mass balance equation. To this, we add the hybrid term again, and the hybrid term serves to enforce weakly the continuity constraints of on the fluxes. In this case, performing the stationarity of this principle, we see as the Lagrangian variable emerge with the physical meaning of fluid potential. Then again, these are the special the space in which the field must belong in this case. And as you can see, before we were using the HDiv broken space. So inside each element domain, we ask our field to belong to the HDiv space. Instead, in this case, because we enforce strongly the mass balance to the substitution of one variable with the other, so we enforce the equation locally inside the variational principle itself, we don't need anymore to require the HDiv space inside each domain. So for this reason, in this case, the flux belong to an L2 space instead. So it's even more, we have even more freedom. So in this case, we again discretize the displacement with a very standard set of shape function. The deformation gradient, of course, depends on that. And then we discretize the fluid potential with 1D isoparametric functions, because it's our Lagrangian variable. So we want to work one side of the element independently from another. And then we have our flux that are described with respect to the local system of reference of each element, as stressed before. So with this set of Cartesian polynomial function. Again, the structure is the same. This time we are in the large strain regime. So this is performed for every Newton-Raphson iteration. This time we need a Newton-Raphson algorithm to solve the system. And again, we can eliminate the flux through the static condensation, and we can recast the problem into a standard displacement-based form. So in this way, we can take the subroutine of the element and give it to a standard solver for displacement-based finite elements. So the framework is fully general. Until now, we have not chosen a free energy density or a dissipation potential of a specific form, under the assumption of the fact that both the solid and the fluid phase cannot dissipate inherently by themselves, but just through the dissipation potential related part. We can choose among the family of them. So in particular, we have chosen here, of course, first we have to split the free energy density under the assumption that we can split it in an additive way. Then we have the so-called effective term that in the pore-elastic framework is related to the skeleton, so the solid response. And we have chosen a compressible Newtonian. For the fluid term, we have chosen a simple quadratic form that works under the assumption of having a perfect fluid. So we have chosen the easiest I will say, expressions for them, just to underline how the formulation works. But then on this, we can build with more complex expression of them. And also for the dissipation potential, that is the function that is related to the passage of, so the flow of the fluid through the matrix structure. We have again chosen the most easy option, so we have this quadratic expression of this dissipation potential. Of course, in this case, the permeability is related to the deformation of the system, because we have this coupled phenomena in the finite-strain regime. From this, we can derive the expression of the first Piola-Kirchhoff, the fluid potential, and the gradient of the fluid potential. So we have again performed the Terzaghi test. In this case, we have performed it in the finite-strain regime, and we have performed a comparison with the gold standard that we have. In our case, we choose to be Abacus, the Abacus element from the commercial software, because we don't have any analytical solution in the finite-strain regime for this kind of problem. So here we performed the same test with different values of the load. So changing the boundary condition, we push farther and farther this column. And we start with being very close to the small strain regime. So you can see as the solution of Abacus, our solution and our solution, but with a linear algorithm. So that doesn't take in account of the nonlinear geometry. They are pretty close one to each other, but then pushing farther and farther, we can see how the two solutions will diverge one from the other, of course, as should be. Then for the same problem, there they were the displacement. Here we have the pressure, as you can see in the case of Abacus, but it's very standard for the so-called UP formulation. We can notice for early time step, or in this case, for a very small level of permeability, an oscillation in the pressure field. That is, the overshooting is way less with this type of formulation. Then another critical test, maybe like from our point of view, the best one is one in which we have 3 layers of material. And in the layer in the middle, we have a permeability value that is 8 order of magnitude less rather than the other 2. So we force a jump in the permeability value. In this way, we can see that as the pressure reaches the interface between the two layers, again, the formulation from the standard UP formulation tends to have this huge spurious oscillation. And I think that this is worse even than the early time step critical scenario when you have such difference in permeability. And we encounter this type of scenario with biological tissues. So for us, it was important to have a formulation that was able to capture accurately the solution, especially in the pressure field for this type of scenarios. So we have presented these 2 possible alternative formulation by recasting the principle through in a minimization principle from a saddle point problem, and then we hybridize it to make it more efficient from a computational point of view. So it is particularly good when we speak of permeability jumps or steep pressure gradients, and we think that a possible development of this formulation is to study also fracture in porous media. Because since standard formulation may have some problem to converge, when there is a jump in permeability, we think that in a scenario in which we have a fracture, and so there is one space in which there is just fluid, and then we have the material itself, because inside the fracture, there will be just fluid, then naturally this will lead to a jump in permeability, because of course at the interface between the fracture and the material itself, we expect to have this huge jump in permeability, and then this may lead to not having a good solution with a standard solver. Since this type of element seems pretty good at assessing a solution in this regime, we think that this may be a good application of this kind of formulation. Especially because in large strain regime, the permeability is coupled itself with the deformation, and then also, of course, the propagation of the fracture will be coupled with the fluid flow, and so with the permeability itself. So in this way, we think that this may help, having this kind of formulation that is flux preserving may help to assess a better solution for this kind of problems. And I will spend my last 2 slides speaking of a problem that we noticed while we were validating the element. So while we were doing the comparison with the Abacus solver, we noticed that standard formulation and also this formulation, at the moment, at least, we are working on that, do not enforce the physical bound of the permeability, and in this way we can have a solution that are physically meaningless, even if they seem regular in terms of primary variable. So just to give an hint on the thing, we start with a description of the Lagrangian porosity that is defined as the ratio between the current pore volume and the reference total volume. Of course, being a ratio between volumes, this means that it has a physical bound. It must be bounded between 0 and 1. And under the assumption of truly incompressibility for both the constituents, that is an assumption that is widely made in literature because it allows to simplify the balance of mass, and so the principle itself and the formulation then, we have that the density, the true density of both the constituent is constant. And for this reason, the sum of the volume ratio must to 1. This is known as saturation constraint. So on the other hand, we need another definition, the definition of point of compaction, because this solution usually it's this thing that the bound of the porosity variable is not satisfied. It happens in the proximity of this so-called point of compaction. So the point of compaction is a deformation state in which the pore space is completely closed. So its definition should be that the porosity goes to 0. And in this way, we have that relationship that you can see in the slide, that J must be equal to 1 minus the initial values of porosity, that is a constant. So technically, according to the constitutive modeling, this bound should always be enforced, and this relationship should be true in the case of reaching the compaction point. However, and of course, under the assumption of truly incompressibility of the solid, we cannot compress more than the compaction point. This is our bound. However, in the case of finite element solution, when numerically we try to assess this problem, if we don't enforce this bound on the porosity variable, and in this moment this is not done, then the saturation constraint may be satisfied only at the expenses of having negative values of porosity. So for this reason, I was saying maybe in a certain range of boundary condition, we see that the solution in the primary variable appears to be regular, even meaningful. We saw this solution and it seemed fine, but then we check on the porosity variable in the Gauss point, and they were negative, so physically meaningless. So we have performed a a little overview on the literature, we searched for that, and actually this issue was already noticed in the past, and possible approaches to address this issue were the use of sort of penalty methods that were included or in the solid skeleton constitutive law. So the free energy density goes to plus infinite if we try to compress more than this point when the porosity reaches 0. Or on the other hand, they were included in the permeability constitutive law. So when the porosity goes to 0, the permeability goes to 0 also. Okay, so the pressure goes to plus infinity. The problem with this idea is that on one hand, they give us physically meaningful result. So they have a physical reason. But on the other hand, if we go just to the proximity of a compaction point, the solution will diverge. So the numerical tool will not give us any solution because will not lead to convergence at all. So in the case of biological tissue, and when we want to simulate, for example, indentation test or perfusion test, it's really easy to go into a compaction point that is maybe not global, so not the whole tissue have the space of the pores that is close, but locally it may happen very easily that some pores tends to close. And maybe we want to go closer to this point. And for this reason, we have this open question for now. Can we try to enforce it in a more rigorous and robust manner instead of using, for example, a penalty method? For example, can we try to recover this bound in a weak form? This would be nice, actually. But this is an open question for now. We are working on that. We hope to have news super soon. But with this open question, I leave you. And I want to thank the other people that are involved in this presentation, because the work was made with them, actually. So Dr. Terzano, Professor Olzaffel, Professor Burino, and Professor Parinello. And here you can find the paper that is related to the linear version of this formulation. The nonlinear one is soon to be submitted. So soon you will have news about it. And with this, I thank you.
Thank you. Okay. Okay, thank you very much, Simona. Are there questions from here or from online? Yeah, Francesco. Do you listen to Francesco?
Very low.
Maybe vicino di un attimo. Come closer. Sorry. Now?
Can you hear me? No. No? Okay. No, I got it. Okay. No, can you hear me now?
Yeah.
Okay.
Ciao.
Ciao. So it was at slide 12 maybe, but also at the in general when you solve the linear systems, and you said that you are able to invert the relations because of the properties of the matrices involved. And since in the final formulation, like the last one, the last line here, no, you have explicitly the inverse matrix KEAA. So you have to compute the inverse of a matrix, and this is usually a computationally very demanding operation. I was wondering if there is if you have ever thought about it, and maybe there's some kind of way to reduce the computational costs of this operation.
Yeah, thanks for the question. Surely, you are right. To invert a matrix, like it has a computational cost. The good thing is that we can invert this matrix locally, element by element. So we work with like small matrices instead of big one. Surely it's a cost, but we prefer to pay this cost because this allows us to not include the degrees of freedom of the stress variables that would be more expensive with respect to invert this matrix element by element. Maybe there are some techniques to avoid even this thing. For the moment, this was our best compromise, but surely it has a cost.
Okay.
It's less expensive than working with the degrees of freedom of the stress, because otherwise you have to include them, and then the element is way more heavier, like computationally speaking, rather than invert the matrix element by element.
Okay, I see. Thank you. And if I can have another question. Since I know that, for example, in biological fluids may be occurring in brain, poroelastic models of brain also take into account some kind of non-Newtonian fluid models. I was wondering whether this approach that you described here could be extended to non-Newtonian flows, or
Surely you can do that if they are not intrinsically dissipative. So if you're including also like some kind of, I don't know, friction, something that then it's related to intrinsic dissipation, then no, the answer is not with this framework in particular. But if they are not non-Newtonian, but they are intrinsically dissipative, then you can surely swap the free energy density related to the fluid with another one.
Okay.
Yeah, maybe I also add a question concerning this, because it's maybe a definition that I do not know. What do you mean with intrinsically dissipative? I mean, a Newtonian fluid is for you intrinsically dissipative or not?
Newtonian fluid, if it's perfect,
Yes.
no. Like, for example, for the solid, a viscoelastic solid will be intrinsically dissipative.
Yes,
for
and a
example.
Newtonian fluid like water with a certain viscosity is intrinsically dissipative.
If behave as perfect, no.
Okay. So you're assuming the fluids are perfect in the model.
Yes.
Okay.
Yes.
Okay. Thank you. Other
This
question?
is related more like if you would take in account also that with the same element you could do it, but you have to change the variational principle. Like that is a problem with the poroelastic framework, that it's like related to this like to being a phenomenological theory. So you can work, but under certain assumption. Otherwise, like the Terzaghi split may not work, for example, because like you have a lot of assumption inside the theory that you can split the stress through this effective term and the fluid term. If you have some intrinsic dissipation, this split may not be thermodynamic consistent anymore. Like it's more a problem of the constitutive framework, the problem of this being dissipative or not, rather than the element itself. Then you could use the same numerical tool, but first you had to write another variational principle instead.
Okay, I get it. Thank you. Are there other questions from here or from online? And maybe just one quick curiosity, because you mentioned that you want to, of course, apply the model to biological tissues, but then you showed us something related to geomechanics. Have you already started doing something with some biological tissue concerning simulation? Have you noticed some differences, something that strange can happen, or it's everything clear?
Not yet.
Okay.
Not yet, because basically our main problem in this moment is the fact that we have developed these elements inside the software FIP that is it's super reliable and it's really good for writing new formulations, but it's also pretty old. So the interface, the graphical interface, and so the generation of the mesh is pretty tough. So to perform simulation on complex geometries, or when you need maybe a really fine mesh, then you have to work on your mesh generator, or you have to change software instead. So for the moment, not yet. The plan is to do so, but not at this moment yet.
Okay. Okay, well, thank you very much. I guess we can thank Simona again.
Thank you.
And then thank all the attendees here and online. And I can maybe finish registration.